Good morning. This is Mr. Wheeler. I thought today we would spend a little bit of time discussing the COVID-19 pandemic. It is now technically a global pandemic. So I've got some dates. So March 13th, there were at that point 1,896 cases, which I'm going to round up to 1,900 cases in the U.S. Okay, now today's April 1st, which is also April Fool's Day. I was thinking my April Fool's joke would be to come up here and say, hey, it was all a joke. Approximately 163,500 cases in the U.S. Okay. So now the equation that's going to govern this type of exponential growth, okay, and when we can say we're doubling every 3 days, that is something that would be an exponential function. So this would be the number of cases. That's going to be y, our independent variable, will be equal to a, the initial amount that we had at some time in the past, and then if it's doubling every 3 days, we could put 2 here, and then for our exponent we're going to have x over 3. That way after 3 days, when x becomes 3, okay, what happens is 3 over 3 is 1, 2 to the 1 power is 2, and we'll have twice as much as we had at the beginning, which was amount A. So this is the number of cases at the start. Okay, now what we're going to do is we're going to plug some of these numbers in, and we're going to figure out if we are doubling every 3 days as suggested by this model. Okay, so the time difference between March 31st and April 1st is 18 days. Okay, so number of days is equal to 18. Alright, so that means x is equal to 18 because x is the number of days. Alright, so what we've got right here is the initial value on March 13th was 1,900. We've got our base is 2 right here, and we've got 18 divided by 3 right there. So first off, let's see what number that gives us, and let's see if that's equal to 163,500. So I take my trusty old calculator that I've got sitting over here right now, excuse me, and let's go ahead and plug our numbers in. Okay, so, and what do I get? I get, let's see, that's 18 divided by 3 is 6, so 2 to the 6th power is 64. 64 times 1,900 is equal to 121,600. Okay, so actually what appears to be happening, okay, so because 121,600 is less than the 163,500 cases we had today, this morning, on April 1st, it appears that it's less than 3 days. Because if it was doubling every 3 days, what we would have, according to our model, is a number that should be bigger than what we have today. So unless right, so let's figure out exactly what that rate is. Okay, so what I'm going to do here is, we know this number 163,500. Okay, that is today's number. We also know we're going to go ahead and take it on face value that was our number back on March 13th. Okay, now what I'm going to do is, it's doubling. What is the rate at which it doubles? So I'm just going to go ahead, I'm going to put a new variable in here. Let's just go ahead and use, I'm going to call it D, lowercase d. Okay, so that d basically is going to be the number of, well, it's going to give me a number that I can use to figure out how long it takes to double, how many days it takes to double. All right, so let's go ahead and do the math here. All right, first step, let's go ahead and divide both sides by 1900. That'll cause it to cancel out over here, and on this side, we're going to get a number over here. All right, so let's see, those two cancel, those two cancel. All right, so what am I going to get? I'm going to get 1635 divided by 19. We can figure out what that number is in a minute. And over here, I'm going to get 2 taken to the power of some number d I don't know. And here's where it gets kind of tricky. Excuse me. Whoops. I mean, it's better like that. Here's where it gets a little bit tricky. I don't really know right now, or maybe you don't, or maybe you do, the operation I can use to solve for d when d is up in the exponent. Okay, so that is a lowercase d. And the way we do this, okay, there's a particular function called the logarithm function. So I'm going to introduce that now. The logarithm function is the natural inverse function to an exponential. So if I say something like this, I'm inventing a function log 2, okay? When I take the logarithm 2 of something like this, 2 to the exponent of d to the power of whatever d is, these two things undo each other and leave me with d, okay? So taking the log to the base 2 of 2 taken to some power will get that exponent down and out from underneath the base, for lack of a better term, and more or less lets you solve when you have d as the exponent, when your variable is actually the exponent of some base number. All right, so we have to do the same thing. It's still algebra, the basic rule of algebra. Whatever we do to one side, we do to the other side. So I'm going to put parentheses around this. I'm going to get my trusty calculator out real quick and figure out what 1635 divided by 19 is. That is equal to 86.05. Okay, so 86.05. I like to keep one or two numbers after the decimal when doing stuff like that. And it's not just this number, it's the logarithm to the base 2 of 86.05. So what that is saying is there is some number, and if I take 2 to that number's power that I'm looking for, that I'll get when I do this operation, I will get 86.02. We know 2 to the, let's see, 2 to the 6th power is 64. We know 2 to the 7th power is 128. So it's somewhere between 6 and 7 is this number right here. And then, yeah, good. Then we can kind of figure out roughly about how long it takes for it to double, since we know that that's also our 18 days right there. Okay, so all right, here we go. So let's go ahead and solve for this. Well, on the right side it's pretty easy. That's just giving us our answer. Now, here's where, if you have a really fancy calculator, there are some calculators that will solve this, where you can input your base for your logarithm function and then the number you're taking. If you don't have that, you have to remember a certain rule of logarithms that says basically this: the logarithm to the base 2 of this number 86.05 is equal to the logarithm to the base 10, which usually we'll not even put the 10 when we write just log. It's understood if we don't put a number, it's to the base 10. And that's what you'll see on your calculator of that particular number, 86.05. And then we have to divide that by the logarithm to the base 10 of 2, the base that we had over here in that particular logarithm. Except this is nice because our calculator does these. So my TI 83 plus that I have right here, we'll go ahead now and show you how to do that on the calculator. So this particular command right here, so just hit clear a couple times. Always like to do that first. All I have to do is log. Okay, there's no 10. It's understood that that's so 86.05 close parentheses divided by log 2 close parentheses, enter, and it gives me this answer where D is equal to 6.427. Okay, so what we have to remember is that 6.427 is equal to the 18 days that we had divided by the amount of time it takes to double. Okay, so what we're getting here basically is saying that we've doubled 6.427 times. We've doubled more than 6 times, but less than 7 times in this whole process. And if we go ahead and leave this as, we'll just go ahead and call this one, we'll call it P for period. So go ahead, we'll solve for P. So D, that doubling kind of number right there, which represents the time interval of 18 days. Go ahead, and that means P is equal to 18 divided by 6.427. And that's going to be, let's do our math real quick on the calculator, equal to 2.8, almost exactly. You can see I got 2.80063 when we took the inverse and multiplied by 18. So 2.8 days right now is the amount of time it's taking the COVID-19 virus cases, number of cases in the U.S. to double, and that's based on the interval from March 13th when we had about 2,000 cases, which also coincides with the day, basically Friday the 13th, that they made the announcement that we wouldn't be coming back to school, that we would be out at that point until April, and now it's been extended to May. So we'll come back and check this every once in a while and see what our doubling rate is every once in a while, see if that number is going down, which would be bad, means it's spreading faster. If that number goes up, it means it's taking it longer to reach more people. So stay tuned. Thank you, and have a wonderful day. Why is it, oh, recording still. Stop.